independent and dependent samples and how we're going to use this to build confidence intervals. Let us start by a few definitions. Two samples are called independent when the sample selected from one population is not related to the sample selected from another population. Otherwise, if there is some sort of association between two samples, you call it dependent. Two samples are called dependent when each member of one sample corresponds to a member of the other sample. For dependent samples, we usually call them paired samples or matched samples. So in different statistics data science books, you might see these two terminologies as well. For independent samples, the visualization is, for example, the number of members in sample 1 is 4, and in the second sample, you have, for example, 7 members. So the number of members in two samples are different. And there is no association between these two samples. However, when it comes to dependent samples, we see some sort of association or relation between members of sample 1 and sample 2. Let me give you an example to clarify this. We're going to classify samples as independent and dependent samples, and then justify why we came up with that dependent or independent relation between samples. For example, sample 1 is the weights of 65 college students before their freshman year begins, and the second sample is the weights of the same 65 college students after their freshman year. In that case, these samples are dependent. Why is that? Because the weights of the same students are measured before and after their freshman year, and they are related. These are the same set of students. The samples can be paired with respect to each student. Another example for you. Now, suppose we have sample 1, including scores for 38 adult males on a psychological screening test for attention deficit hyperactivity disorder. So in the first sample, you have the score for 38 adult males. The second sample is the scores for 50 adult females on a psychological screening test for attention deficit hyperactivity disorder. The size of the first sample is 38. The size of the second sample is 50. And you have two groups of people participating in this test. These samples are independent from each other. It's not possible to form a pairing between the members of the samples. The sample sizes are also different from each other, and the data represent scores for different individuals. So here I gave you two examples. The very first sample, which is the same groups of students, is a dependent sample, and the second set of samples are independent. Now, how are we going to use this to construct confidence intervals? We need some basic assumptions. First of all, we're going to take two samples, and these two samples must be independent from each other. Number two, both samples are simple random samples. Number 3, either or both of the following conditions is satisfied. The two sample sizes are both large, each sample size is more than 30, or both of these samples are taken from populations that have normal distributions. For small samples, the normality requirement is loose in the sense that the procedures perform well as long as there are no outliers and there isn't a strong skewness. Now, in constructing the confidence interval, estimating the difference in population means, in the very first case, we're going to consider independent samples. And basically, we don't have any information about population standard deviation. The confidence interval estimating the difference in population means mu1 minus mu2 can be written this way. The difference between population means is bounded between the difference in sample means minus the margin of error, and upper bound is the difference in sample means plus the margin of error. The margin of error formula is you have a critical value, t, times the square root of the variance of the first sample divided by n1 plus the variance of the second sample divided by n2. You can use t-table to find this critical value. The degrees of freedom is the smaller of n1 minus 1 and n2 minus 1. So this is the case that you have independent samples and you don't have any extra information about population standard deviation. In the second scenario, you have independent samples and you know that the population standard deviations from past studies are equal to each other. In that case, we're going to use pooled variance. The difference in population means is bounded between the difference between sample means minus the margin of error and the difference between sample means plus the margin of error. In order to calculate the margin of error, we're going to use a different formula. First, we find the critical value, t, and then multiply that by SP squared, which is the pooled variance over N1 plus SP squared over N2. And the way that we calculate the pooled variance is N1 minus 1 times the first sample variance plus N2 minus 1 times the second sample variance divided by N1 minus 1 plus N2 minus 1. The degrees of freedom is going to be N1 plus N2 minus 2. So as you can see, I gave you two different formulas. For the first formula, the margin of error is the critical value times the square root of the first sample variance over N1 plus the second sample variance over N2. And the degrees of freedom that you're going to use is the smaller of N1 minus 1 and N2 minus 1. However, if the question says, well, we have some sort of information about population standard deviation, these two numbers are the same. In that case, you're going to use a pooled variance. Use the pooled variance to calculate the margin of error. And the degrees of freedom that you're going to use is N1 plus N2 minus 2. Now let us begin one example. Our goal is to construct a confidence interval estimate of difference between 1988 heights and 2012 heights. So we're going to find the difference between these two means. We're going to construct a 90% confidence interval estimate of the difference between the mean height in 1988 and the mean height in 2012. We're going to take the very first sample, including 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 members from 1988. So this sample is taken from the first population, and we need another sample taken from the second population. For the second sample, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So your second sample has 15 members in it. Let's begin the process. For manual calculations, we're going to first find the value of the margin of error. In order to find the value for the margin of error, we need to find the critical value. Remember that we don't have any information about population variances or standard deviation. We're going to use our table, t-table. We're going to use the degrees of freedom of the smaller value, which is 11. Alpha is 5% on one tail, and the critical value that we calculate is 1.796. Please note that this is just using the table. If you use calculator or Python or any other software, you're going to get a more accurate value. Remember our t-table. For the t-table, when the degrees of freedom is equal to 11, we are looking at this line. And please note that since we are constructing a 90% confidence interval, the area on one of the tail is going to be just 5%. So it means that we are matching that with the 5%, or basically when you have confidence level, some tables don't have the confidence level. You just need to identify the 5% of the area on one tail, and here you get 1.796 as the critical value, which is your t-value. Let us move on to next slide. So as we used the t, which is our critical value of 1.796, the sample statistics N1, we have 12 members in the first sample, and S1, after doing the calculation, is going to be 66.60. N2 is 15. We have 15 members in the second sample, with standard deviation of the second sample to be 47.866. We're going to use this to evaluate the margin of error. Remember the formula for the margin of error. Margin of error is the critical value that we calculated, 1.796 times the square root of the first sample variance over N1 plus the second sample variance over N2, which we calculated as 1.796 times the square root of 66.612 to the second divided by 12 plus 47.866, 18 to power 2 divided by 15, or as you can see, the margin of error is about 41. Now we can move on and find the difference between population means, which is going to be the difference between sample means minus the margin of error, and difference between sample means plus the margin of error. All of these needs to be X bars. Let me add these bars as well here to avoid any confusion. X1 bar, X2 bar, and now the difference between population means is in between negative 79.4 and 2.7 on the right-hand side. So basically, what do we have? The difference between population means includes 0. the confidence interval limits of -77.9 and 1.1 found from technology are also more accurate. But since we are just using our table and doing calculations manually, this is the result that we are getting. So when you're using Python or other softwares and you get different values, as long as they're close enough, we should be fine. But what's the meaning of this? When we see that the difference between population means is bounded between these two numbers, what's the meaning of that? We say that, hey, we are 90% confident that the confidence interval actually contains the difference between the mean height in 1988 and the mean height in 2012. So, since the confidence interval does contain 0, it suggests that there isn't a significant difference between the mean heights in two populations. So again, as long as your confidence interval contains 0, it means that there is not a significant difference between two population means. So that's how we calculate the confidence interval for the difference between population means.